here we have a picture of the wave, of a wave, arbitrary wave, no scale specified or anything, but we have an x-axis here, meaning we're showing the wave in space, and we're showing it at its maximum displacement. That's our assumption. This is maximum displacement. So the displacement at a position of maximum is the amplitude A. Now, the equation of this wave is y equals a sine of kx, where k is a constant, as you recall, that's directly related to the wavelength. Again, we're being unspecific about the wavelength at this point. So we're being unspecific about k, except that k is related to the wavelength. When kx changes by 2 pi radians, we've gone through a complete cycle, so the wavelength is going to be 2 pi divided by k, whatever that happens to be. But we don't need that right now. Okay, the whole point is, here's a spatial picture of the wave at a maximum amplitude, and there's another possible spatial picture of the same standing wave at a maximum amplitude where the maximum displacement is on the other side of the axis, so that this peak would become a valley, this valley would become a peak, the wave would look like this. Okay, well, so here's a snapshot at the time of maximum displacement, and the equation of that wave is a times the sine of kx. Now, if we look at a specific position x here, then the particle at this position is not going to go to this displacement from equilibrium. It's only going to go this far from equilibrium because, of course, this picture shows maximum displacement from equilibrium. Maximum displacement of the point at position x is just this, as opposed to the full amplitude. And of course, what is this? Well, by the equation of the wave, we plug x in to the equation of the wave, and right there is the maximum displacement at position x. Okay, well, we're going to have simple harmonic motion at every point. Okay, at every point of this wave, you're going to have a simple harmonic motion with angular frequency that we'll call omega. So that the ultimate equation for y in terms of both x and t is y equals the amplitude at position x multiplied by the sine of omega t. And of course, we understand the function of the implications of the sine of omega t for simple harmonic motion. So we multiply amplitude times sine of omega t, and we have a simple harmonic motion of a point. Well, what's the amplitude at x? It's a sine of kx. So that's a sine of kx multiplied by the sine of omega t. And that's the equation of this entire wave. So we can say that more explicitly. Y of tx equals a sine of kx times sine of omega t. Now, this equation satisfies the wave equation. This is the equation of the wave. The wave equation is your partial differential equation. I'm not going to go through the details of taking the derivatives of this partial differential equation. I'll just point them out. If you're taking the second partial with respect to t, the only t dependence is in the sine of omega t. And if you take two derivatives of the sine of omega t, you get negative omega squared times the sine of omega t. And the result that you can verify is that that equals negative omega squared times the entire function. In other words, chain rule and everything, you only get a negative omega squared by taking two derivatives with respect to t. And the whole thing's going to be multiplied by that. Okay, second partial of y with respect to x, you're going to get a negative k squared out of this. And again, you work through the details. You should understand that pretty easily, but you probably, most people are going to have to write that out to really understand what I'm talking about. And in any case, this is negative k squared times your y function. I could have written all the a sine kx and sine omega t instead of the y of kt, but for brevity, I wrote it out more simply this way. Now, to see that This gives you the wave equation. The second partial y with respect to t divided by second partial y with respect to x should give you the propagation velocity. Well, from what we see here, it's obvious that you're going to get, when you do this division, this divided by this is just going to be omega squared over k squared, which we have here. And what's omega? Omega, remember, is 2 pi times the frequency. Omega is 2 pi times frequency. Okay? And that's simple. Frequency is how many times you go around the reference circle per unit of time. Omega is how many radians per unit of time. And every time around the reference circle is 2 pi radians. You put that together, write it down if you need to, reason it out. Something you have to understand at a gut level, not just by quoting a formula you don't understand, okay? So omega is 2 pi f. We can always pull that out if we understand the circular model and what frequency means and what angular frequency means. Kx. When x changes by lambda, Kx has to change by enough to make the sign go through a full cycle. So that K times lambda has to equal 2 pi. K is then 2 pi divided by lambda. So just from this expression and the fact that a change of one wavelength has to drive this through a complete cycle, we deduce that K is 2 pi over lambda. So that omega squared over K squared is what? It's 2 pi f divided by 2 pi over lambda. Of course, that'll be squared. And that's going to be f lambda squared. And if you understand the relationship between wavelength and frequency, how many cycles you get in a unit of time, how far you go for every cycle. If you multiply how many per unit of time by how far you go for each one, you get how far you go in a second. And that equals c squared. Now, I think I said a minute ago that this should equal the velocity. It's equal to the squared velocity. And very briefly, if this holds, if this divided by this is equal to c squared, then the usual, most common expression of the wave equation, second partial y with respect to x, is reciprocal of the propagation velocity squared times the second partial with respect to t. In any case, this function satisfies the wave equation just as the function for a traveling wave satisfies the wave equation.